The journey begins long before the peppers are packed. Before they're sorted, cooled, or loaded onto ships, they are still breathing. Peppers, unlike inert cargo, don't stop reacting the moment they leave the field. Each one is a living cell, cluster, releasing capsaicin, expelling moisture, and producing heat. It's a metabolic dance that continues even after harvest. Inside the confines of a shipping container, this dance becomes a thermodynamic paradox, a cargo that warms itself, sweats through its skin, and quietly battles its environment. Every shipment is a controlled gamble against biology, physics, and time. Managing that gamble requires precision that rivals aerospace calibration. A temperature drift of just 0.4 degrees Celsius may seem insignificant, but in the sealed atmosphere of a transatlantic container, it's enough to tilt the balance. Moisture begins to form on the skin of the fruit. Condensation collects, not across the cargo, but in micro pockets. There, fermentation silently takes hold, and with it, the decay of firmness, of flavor, of market value. It's the same principle engineers use to calibrate hydraulic nozzles on automated sprayers. A single micron of pressure deviation, and the chemical distribution across a crop becomes erratic. The analogy is precise, and it matters. Tiny variables, massive consequences. But the flaw is not only in how we measure, it's in how we imagine. Most people see crates of peppers as fixed units, static, stacked, and motionless. But in truth, each one is a thermal cell. Heat rises through the stack unevenly. The upper layers overheat, the lower ones remain cold. This is thermal stratification, a concept well known in naval engineering. Inside marine engine rooms, heat is managed by deck layer zones, ventilated by system-controlled air ducts that adapt minute by minute. Yet in pepper logistics, that same layered thinking is often ignored. We treat the container like a uniform box, when it's a matrix of differential heat fluxes. And so the question isn't rhetorical, it's strategic. If naval engineers are expected to balance thermal load per deck, why are fruit exporters still cooling their cargo as if every crate is identical? Why is pepper freight not treated as a thermally complex body, but as bulk produce in a cold box? Somewhere between the design of an air-cooled turbine and the shelf of a supermarket, we've missed a crucial truth, that what seems simple in transit may be thermodynamically volatile in practice. The heat, the capsaicin, the moisture. They're not flaws, they're signals. They're data points that ask us to recalibrate not just the systems we use, but the mindset with which we ship food across the planet. Because every pepper is still alive, and every container is a battleground of invisible energy. Inside the sealed world of refrigerated transit, peppers are not only exposed to temperature, they are immersed in microclimates shaped by the very crates designed to protect them. As external humidity rises and air movement slows within container walls, an unexpected reaction begins: micro-fermentation on the surface of the fruit. This is not fermentation as in flavor development, but a slow, irreversible breakdown of structure and skin integrity. It happens quietly, often invisibly, where the crate wall meets the curve of a pepper. The design that supports mass transport also creates still pockets of air, and that stillness is the perfect environment for decay. The response to this problem is no longer hypothetical. Over the last 5 years, a new generation of transport crates has emerged. These aren't just perforated plastic boxes, they are engineered environments. Liners infused with hydrophobic polymers actively repel moisture, redirecting it through wicking channels that carry condensation away from contact surfaces. In trials, these crates have reduced visible mold by as much as 40%, not through chemicals, through airflow, through design that understands the nature of biological cargo. Living, respiring, always. But design alone is not enough. Exposure matters. Field data reveals a surprising correlation. Peppers packed with less than 18% of their surface exposed to direct airflow degraded nearly 3.5 days faster than those exposed in the 28 to 33% range. It's not about leaving them open to the elements. It's about avoiding stagnant air. In tight crate designs, moisture becomes trapped between fruit bodies, forming high humidity pockets that act as fermentation chambers. The crate becomes a container of silence, and silence becomes... In Morocco, one export company decided to intervene. Instead of focusing on container ventilation as a whole, they mapped airflow at the crate level. Every curve. Using aerodynamic models typically applied to car design, they adjusted crate angles, changed perforation sequences, and redirected air with baffling insight. Over 3 harvest cycles, mold loss dropped by 22%, not with chemicals, not with refrigeration upgrades, but with shape, airflow, and rethinking what a crate is supposed to. Because in pepper logistics, control isn't about lowering the it's about understanding where the temperature goes once it's inside. It's about managing the way air curves around each fruit, the way condensation moves, the way moisture rests. It's a geometry of freshness, a math of respiration, and the goal is simple. Reduce the silence. Let the air flow, not across the but through the pepper's world. One crate, one angle, one curve. Check the pinned. Precisions. In the world of refrigerated logistics, numbers create a sense of control. A container reads 8 degrees Celsius. The logs confirm ability. The shipment prints. But within that calm, an illusion persists. The illusion that average temperature tells the whole. What it hides are the silent anomalies. Those 2 or 3 degrees of localized heat trapped in a corner crate where airflow failed to reach and respiration doubled in risk. These are not errors in refrigeration. They are oversights. The biology inside each crate does not respond to the average. It responds to the microclimate. This invisible fragility is becoming durable. With the rise of IoT-enabled logistics, sensor grids can now be deployed across the vertical and horizontal layers. Tiny nodes detect not just temperature, but differentials, air velocity, moisture gradients, thermal. When linked to a dynamic control system, these sensors allow air distribution to adjust in time. If one crate begins to heat faster due to metabolic load, the system responds. The airflow shifts, not across the entire container, but to that specific region. It's no longer about cooling cargo. It's about managing thermal feedback loops inside the living system, and the data is expected. Containers calibrated to maintain a fixed 8-degree average showed up to 17% higher spoilage than those that allowed slight fluctuations, but with stratified airflow that adapted zone to zone. The biological reality is counterintuitive. Uniformity can accelerate decay, but variability, if controlled, creates resilience. The pepper breathes easier, moisture dissipates, spoilage slows, freshness lasts longer, not because the temperature is lower, but because the environment inside becomes active, intelligent, and responsive. This principle has moved beyond. In the Netherlands, a high-volume exporter reimagined its container architecture with thermal zoning in mind. Each pallet was mapped according to airflow resistance and product respiration rate. Instead of flattening the temperature profile, they designed a climate that pulsed, shifting like a lung, adjusting like an irrigation system. In a 12,000-kilometer shipment, shelf life doubled. Not with chemicals, not with refrigeration upgrades, with logic, with microthermos. Because the true model isn't refrigeration, it's. Each crate becomes a thermal cell. Each pallet. The cargo behaves like a network. And like a data center, it must be cooled not as a mass, but as a system. Each unit mapped, monitored, and kept within biological tolerances. The lesson is not that peppers are delicate. It's that they are precise. Their journey doesn't end with harvest. It becomes a sequence of thermodynamic equations, and in each equation, the variable is no longer temperature alone, it's intelligence. Thermal intelligence, distributed across the cargo like thought circuit. Alive, responsive, constant calculating. On a precision-managed farm, no drop of water falls randomly. Across hectares of land, variable rate irrigation systems distribute moisture with a logic that borders choreography. Every nozzle, every interval, every pressure variation is calculated based on real-time soil feedback. Sensors buried beneath the roots detect humidity, density. The system adapts, not once a day, but in constant micro-adjustments. A slope 2 meters wide may receive 12% less water than one beside it, simply because it drains faster. This is not automation for its own sake. It is reactive agriculture, tuned to the quiet needs of each of Earth. Every square meter is different, every decision deliberate. This philosophy, responsive, localized, deeply intelligent, has reshaped how we grow food. And yet, once those peppers are harvested, once they leave the soil and enter the vast choreography of global logistics, this intelligence is too uninterrupted. The variable becomes uniform. The adapt is static. Inside the cold chain, airflow is typically set once, calibrated to a general target temperature, then left to act as a blanket over dozens of pallets. But a blanket is not what a living cargo needs. Peppers are not inert. They breathe. They off-gas. They release heat. And like the land they grow on, each crate, each layer, each corner of a container behaves differently. What cooling systems require is not more power, but more sensitivity. Some operations are already embracing this transition. In the distribution hubs of Amazon Fresh, cold chain logistics are beginning to mirror the logic of precision agriculture. Using artificial intelligence integrated with real-time sensors, the air inside refrigerated units is adjusted not by fixed schedule, but by evolving biological feedback. Every 12 minutes, airflow is recalculated, not only to reach a numeric temperature goal, but to respond to the packaging density, the rate of respiration, the geometry of the cargo itself. The system reads the breath of the fruit, it tracks the heartbeat of the produce, and it adapts. Not like a refrigerator, like an organism. This is the mindset shift pepper logistics now demands. To stop regulating by container volume and start managing by thermal signature. A truck, a ship, a container. They must be thought of not as static boxes, but as dynamic biospheres. The peppers inside are not units of freight. They are thermogenic emitters, each influencing and being influenced by the microclimate around them. Cooling them effectively means understanding how they behave together, how their respiration rates fluctuate depending on stack height, proximity, density. One pepper does not behave like 100, and 100 do not behave like 1,000. The scale changes the biology. To implement this, we need to think in layers, much like how irrigation systems respond to surface runoff, soil porosity, and absorption gradients. Cooling systems must respond to airflow impedance, metabolic clustering, and vertical thermal drift. A pepper crate positioned near the container wall behaves differently than one in the center. A lower crate, compressed under weight, may trap more humidity than one near the top. These are not secondary effects. They are primary factors in post-harvest degradation, and they demand a structural response. Imagine a logistics operation that treats each pallet like a precision farming plot, each one equipped with sensor nodes that measure temperature, humidity, and gas concentration. A control algorithm learns the profile of that pallet, its resistance to airflow, its likely points of heat accumulation, and as the container moves through different climates, port, highway, customs delay, the airflow changes, not globally, locally. Ventilation valves redirect air, not just through the container, but through specific corridors where pressure differentials have emerged. Moisture is vented away before it condenses. Heat is drawn out before fermentation begins. The result is not just fewer spoiled crates. It is a deeper freshness, a sustained biochemical equilibrium. This is not speculation. It is the logical evolution of agricultural technology. We have already accepted that no farm field is uniform, that no irrigation system should treat clay like sand or hilltop like base. Now, we must accept the same in logistics. No container is truly homogeneous. No shipment is truly stable, not unless we make it so. Because the future of food logistics does not lie in stronger engines or colder systems. It lies in adaptation, in cargo environments that think like ecosystems, in cooling that behaves like smart irrigation, localized, responsive, continuous. We already map soil. We already map water. The next frontier is mapping heat, mapping respiration, mapping time. And in that future, freshness will no longer be protected by guesswork or averages. It will be preserved by intelligence, technical, distributed, invisible, yet everywhere. From the farm to the freighter, from the sensor to the wig, shelf. The precision that begins in the soil must follow the food until its very last month. Because freshness is not a condition, it is an engineering achievement. And like all great achievements in agriculture, it starts with understanding, not of what we ship, but of how it lives. And while you're here, take a moment to check the pinned comment. Sometimes, what's most worth discovering isn't in the video. It's just one click below.